So, as Vector, the villain, pointed out to us, a vector is a directed line segment, so it's like an arrow. It has both magnitude and direction. Maybe next to where you're writing that, go ahead and draw an arrow. Where the arrow starts is what we call the initial point, and where the arrow ends is what we call the terminal point. I'm sure if I used those words, you could probably figure out what I was referring to without that picture. But it does make a difference which one is initial versus which one is terminal. Okay, if we're going to talk about that next bullet point, equivalent vectors, what has to be true about vectors if they are going to be called equivalent? Magnitude is the same, direction is the same. Okay, they both have to be the same. And we're going to look at some pictures where they're not the same. But the magnitude, which is notating the length, and the direction, they both have to be the same. Okay, so I have 4 pictures that I'm going to show you of the comparison of 2 different vectors. Okay, my first 2 pictures here. Here are 2 equivalent vectors. You can see that they're going in the same direction. They're parallel and pointing in the same way, and they're the same length. Okay, these vectors here that are in black, they have the same magnitude, and I show that to you by showing them parallel, okay, but they're going in different directions. And they don't have to necessarily be parallel to be in different directions, it's just easier to see that they're the same length, okay? In this particular drawing, what would we say about those 2 vectors? They're going in opposite directions, and that'll be important here soon. Okay. Here are 2 vectors that have the same direction. Okay, they're pointing with the same angle. However, they are different lengths. And then here are 2 vectors that just have nothing in common. Okay. But as you can see from these 4 pictures, the only time they're going to look the same is both direction and magnitude are the same. Okay, now we can draw vectors anywhere in the plane. Okay, but when we work with vectors, we like to work with them in standard position. That way we can compare them to other vectors. Okay. So when I talk about standard position, I'm talking about a vector with its initial point at the origin. Okay, here's its initial point at the origin. If you want to draw the picture, there's the picture. Wow, that yellow does not show up very well, does it? There we go. Okay, so a lot of what we do today is we have to talk a lot about the vocabulary about vectors, okay? How do we find magnitude? How do we find direction? What are some special things that vectors have that we can use to help us? So first we need to know how to write them, okay? So component form refers to a vector in standard position. And we use these chevrons, okay? They're those kind of arrow-looking things point. So instead of parentheses, we're going to use the chevrons. Okay, so we have x2 minus x1 and y2 minus y1. What do you think I'm referring to there? Okay, good. When we are finding the different components, we need to take the terminal point and subtract the initial point. Okay, that's how we're going to get each component. So if it is not already in standard form, then we need to use terminal minus initial for the horizontal component, terminal minus initial for the vertical component. If your vector is already in standard form, then vector V, you would see a vertical component and a horizontal component. So it's going to look a lot like an ordered pair, but it's going to have the chevrons, which is how we know that it is a vector. If you need kind of a picture of what that looks like, if I gave you the vector 2, 3, okay, remember component form, that's giving it to us in standard position. So the vector 2, 3 would look like this. We have a horizontal component of 2, vertical component of 3. There's the vector 2, 3. Okay, it's just plotting that point and drawing it in standard position. All right. Vectors have magnitude and direction. Okay. Magnitude is very straightforward. Magnitude refers to the length of a vector. So what I want you to do, okay, first of all, when you see double absolute value bars, that is referring to the magnitude of the vector. Okay. And we're going to create a formula with the vector AB. I want you to have a 30-second conversation at your pod. How do you think we're going to find the length of the vector if we know the horizontal and vertical components? Okay, go ahead and have a conversation. Go. Okay, pod 1, what did you discuss? The Pythagorean theorem. We know that our horizontal component is A. We know our vertical component is B. So if we use the Pythagorean theorem, we can get the length of that vector. Okay? So A squared plus B squared equals hypotenuse squared. Do you agree? So the hypotenuse, aka the magnitude of V, is going to be the square root of A squared plus B squared, where A is representing our horizontal component and B is representing our vertical component. Okay. So we're going to jump to that example that's next to both. Well, it's really more next to the component form, but it's the example. Well, it's the example where we have an initial point of negative 2, 3 and a terminal point of negative 7, 9. Okay, this is nice. I don't have to wait for you to write down the problem, right? Okay, so in order to find vector V, and do you notice how the letter V is bolded? Vectors are named with bolded letters. Okay, so if it is a vector, it will be folded. Okay, so vector V, to put it in standard form, or in component form, excuse me, the process we need to take, what do we need to do with those two coordinates, Tiger? Okay, terminal minus initial for our x component, terminal minus initial for our y component, or a vertical component. So vector V would be negative 5, 6. Which quadrant does vector V live in? What? Second quadrant. Okay, good. Now, if we're going to find the magnitude of V, okay, remember it's those funny absolute value bars, it's like the double, okay? The magnitude of vector V, we just have to use the Pythagorean theorem. So the square root of negative 5 squared plus 6 squared. Okay, so I'll ask that you just tell me, let's see, 25 plus 36 would give us 61. So we can just leave it as the square root of 61. That's fine. And then fix that. All right, what do you think? How many of you have done that exact same process in a science class? What about the magnitude? No? Not like that? What do you do in science?
They give us the magnitude and we have to find one for the space or something.
Oh, okay. So this is kind of like backwards. Gotcha. Okay. Our next topic is a unit vector. Okay. A unit vector. Okay. Remember how our unit circle was a circle with radius 1? Our unit vector is a vector with magnitude 1. Okay. When you hear the word unit, I want you to think of the number 1. What? It will be small in comparison to what we just did. If you zoom in, it's not so small, right? Okay, so it can be very beneficial for us to have a unit vector because the magnitude is 1. So we need to be able to take a vector and find a vector in its same direction, but with a magnitude 1. Okay, so I'm going to give you a vector V, and I want it to be in the same direction, but I want it to be, I want it to have length 1. Okay, so essentially what we're working with here is this picture. Okay, here these two are going to have the same direction, right? But I'm going to take this vector and I'm going to make it smaller, or maybe bigger. I don't know. Okay. Any thoughts on what will be true about vectors that have the same direction? Or can you think of two vectors that have the same direction? Like, can you give me an example? Brainstorm with your thoughts first. That way it's not scary. Okay, any thoughts on vectors that have the same direction? I drew. They're gonna have the same slope, yes, which means, like the vector 2, 4 would have the same direction as the vector what? Caleb? Well, what would have the same slope? Give me another vector with that same slope.
One, two.
Perfect. 1, 2, and 2, 4 are in the same direction because, as he described, they have the same slope, right? If we look at the vectors, they're scalar multiples of each other, right? We can take 1, 2 and multiply it by 2 to get 2, 4, 3, 6, 4, 8. All of those are scalar multiples of 1, 2, which means they'd all be in the same direction. Yes? I would not say proportional. I would just say in the same direction.
If we knew like the sides of one, could you make it into a triangle and be like proportions?
Yes.
One?
I suppose in that fashion, yes. Because they would have the same angle. Okay, they'd be similar. Okay? So what we need to do is we need to take our vector and we need to multiply it by a scalar so that our magnitude is 1. But by multiplying by a scalar, we are still in the same direction. So how we're going to do that is this right here. We're going to find the magnitude and we're going to multiply our vector by the reciprocal of the magnitude. Okay. Now, I do want to make a note, and you don't have to write this down. This is what we've been talking about. Whatever we get here is going to be a scalar multiple of b, and because of that, they're in the same direction. All right, that's what we just talked about. No need to write that down. So here we're going to go to the example in the box next to it. I am giving you the vector 7, -3. Okay? I want a unit vector in this same direction. So the first thing we would need to find would be what? We need to find the magnitude, okay? Everyone find the magnitude of b for me. Magnitude. Richard, what do you get for your magnitude?
58.
Square root of 58? Do you agree with Richard? We have the square root of 7 squared plus -3 squared. Okay? Good? So, our unit vector, and I'm just going to call it u for unit vector, we're going to take 1 over square root of 58, and that's our scalar multiple for vector v. Okay, so we would multiply that through and rationalize the denominators. So we would have 7 square root of 58 over 58, comma, -3 square root of 58 over 58. Okay, if we found the magnitude of this vector right here, it would be 1. Okay, if you think about it, we know that the magnitude of this vector is square root of 58. So when we multiply square root of 58 to 1 over square root of 58, we're going to cancel to be 1. Okay? That's why we set it up the way that we did. All right. Let's talk some good physics here. Adding vectors together. Okay? Go ahead and turn your sheets over. We are going to do some vector operations. Now, You have a note on your note sheet there that there are some properties on page 421. This is what they are, okay? Just kind of talking about commutative, associative, identity, inverse properties, all with vector addition, okay? I don't think it's anything that you wouldn't assume anyway, okay? So if you want to reference those, you can, but like I said, I think they're all fairly intuitive for what we know about addition and multiplication anyway. Okay. All right, so the first thing, scalar multiplication. Okay. Scalar multiplication means we have a vector and we multiply it by a number, just kind of like we did. Okay. But what's going to happen if the scalar is negative? What's going to happen to our vector? Okay, good. So it's going to change direction. Okay, so if we have vector v, negative vector v is just going to go in that opposite direction. Okay, so it's okay. If you want to draw any pictures to the left of these, you can, but it's not a requirement. Okay, vector addition. Okay, geometrically, we are going to put the initial point of the second vector at the terminal point of the first vector. Write it down and I'll show you what that looks like. Okay, we're putting the initial point of the second vector at the terminal point of the first vector. Okay. Here's our picture. U plus v. If I have, excuse me, vector u, then to add vector v, I'm going to put the initial point at the terminal point. So I'm going to like connect them, but keeping them in that same direction, whatever they are. When we connect the initial and terminal points that aren't already connected, that is u plus v. Physics. Is that something that you did in physics? Okay. Excellent. Okay. What are we going to do about subtracting vectors? How's that going to look different? If I'm going to take u minus v, then what needs to be true about that second vector? What? It's not going to have to be bigger. If we think of u minus v, okay, geometrically we're thinking of u plus negative v, right? And what happens when we put a negative sign in front of a vector? It's going to go in what direction? Opposite direction, okay? So if we're going to subtract two vectors, the second vector is basically just opposite, okay? So we have u minus v, we're going to take v, make it go opposite direction, and then find it, okay? That's all geometrically, okay? Whatever we get as an answer is what we call the resultant vector, okay? I say that with emphasis because that's the language your book is going to use. Find the resultant vector. I need to know what the resultant is. It's just the answer of an addition or subtraction problem. Okay? So we're going to go off to the right, and we're going to do that big example box that you have there. Okay? Now let me get you something quick. Okay. With numbers, it is as simple as adding the components. Okay? U plus v. We're going to add the horizontal component. We are going to add the vertical component. Our resultant vector is 4, let's try 4, 6. Okay. Now, if you want the picture, some of us appreciate the picture. Okay. Vector u is 1, 4. So 1, 2, 3, 4. Here's vector u. And then from that terminal point, we're going to draw vector v, 3, 2. So from here, I'm going to go over 3 up 2. And so then our resultant vector is that vector 4, 6. Okay, that's why geometrically it's working out the way that it is to get the 4, 6. Next, let's take u minus v. Some of you maybe have even worked ahead and already figured out what u minus v is. Okay, yes, it is as simple as taking 1 minus 3 for the horizontal components and 4 minus 2 for the vertical components. In a picture, here's vector u, and then we have to add the opposite of v, so we're going to have to go over 3, down 2, and there's our vector 2, 2. And then last but not least, 2u minus 3v. Okay, 2 and 3 are just scalars for those vectors. So if vector u is 1, 4, minus 3 times vector v is 3, 2. Okay, all we would need to do is distribute that 2 through vector v. Distribute that 3 through vector v, and now we have a subtraction problem. 2 minus 9 is negative 7, 8 minus 6 is 2. We have 2 more concepts to talk about and we're done. Okay. Okay, we have what is called standard unit vectors. Okay. Unit vectors have magnitude what? 1. Okay. Here are your 2 standard unit vectors. Vector I is the vector 1, 0. Vector j is the vector 0, 1. Notice how each of them have magnitude 1, but they only have one component. So vector I is only horizontal, and vector j only has vertical. This gives us the ability to rewrite a vector as a linear combination of vectors I and j. Okay, you've been around this math game long enough to know that there are different ways to represent the same thing. Okay, it doesn't happen to us often, but we do know that it is okay to have multiple ways to represent something. Okay, there's also multiple ways to solve problems. Okay, in vectors we have 2 different ways to represent a vector. Okay, component form looks like this. But then we have something called linear combination form, okay? So if we have a vector, v1, v2, we would write it as that horizontal component times vector I plus the vertical component times vector j. There's no chevrons, there's no comma, it's an addition problem. Horizontal component times I, because that is the horizontal unit vector, plus vertical component times j, since that is the vertical unit vector. So we're going to try it out with this example right here. So we have an initial point of 5, 2, and a terminal point of -3, -1. First thing I want you to do is write it in component form for me. Please write this vector in component form and compare it to your neighbor. Compare it to your neighbor. Tegan, what do you have?
I got -8.
Tegan has -8, -3. Do you agree? Yeah? Okay, good. Terminal minus initial, terminal minus initial. So now, the linear combination part of it, we would write vector v as -8i minus 3j. It's just a different way to represent the vector. We're still thinking about it in standard position. It's just a different way to represent it. Mrs. Holman, what does any of this have to do with trigonometry? I really felt like we've used a lot of trigonometry yet. We did like the Pythagorean theorem, right? That was pretty simple. Okay. Let's finally talk about the direction. The direction angle is the measure of the angle between the vector and the positive x-axis. Okay, so you see my picture there? I really got to change this yellow vector. Here I have a vector, and we are looking for theta. If we know vector AB, what trigonometric function could help us? We know vector AB. All right, we know that our horizontal component is A and our vertical component is B. Therefore, the tangent of theta should equal B over A. Okay. Only thing I need to warn you about is two things I need to warn you about. A, I only want angles between 0 and 360. Okay. B, the range of inverse tangent is -90 degrees to +90 degrees. Your angle or your vector could lie in quadrant 1, 2, 3, or 4. So you're going to have to use some reference angles to get the actual angle between 0 and 360. Okay? Let's do 2 examples and I will show you what I mean. Let's first do the example 3, 4. Okay, that's your first example to the right of direction angles. Okay? If we have a vector 3, 4, so 1, 2, 3, 1, 2, 3, 4. We're looking for theta right here. I know horizontal component 3, vertical component 4. We need, tangent of theta to be 4 over 3. And guys, it's always going to be vertical over horizontal, right? That's how it is in the unit circle, sine over cosine, vertical over horizontal, okay? So, in your calculators, please take the inverse tangent of 4/3. Chris, you have something? Or do you have a question?
Are the calculators supposed to be in degrees or radian though?
Degrees, please. Degrees, please. Courtney, what'd you get?
55.1.
55?
Or 53.
Okay. At first I was like, oh, did I write that down? Okay. 53.13, do you agree? Excellent. 53.13, quadrant 1 angle. Is this in quadrant 1? Excellent. Second example, negative 3i minus 10j. Which quadrant is that in? That is in quadrant 3, where we are looking at that angle right there. Okay? So we're still going to take the tangent of theta is equal to negative 10 over negative 3. Okay? It's always going to be vertical over horizontal. When you take the inverse tangent of 10/3, yeah. Lindsay, did you type it in your calculator?
Yeah.
What do we get? 73.30. Is that describing the angle for negative 3i minus 10j? It is not. That is a first quadrant angle. That's all you're going to get out of the inverse tangent. So, in order to get this actual angle, what do I need to do with 73.3? Since we're in quadrant 3, we need to add that to 180. So that's actually our reference angle. So theta is actually, since we're in the third quadrant, 180 plus 73.3. So our angle is 253.3. Okay, so you're always going to get an acute angle out of inverse tangent. That is your reference angle. Make sure you're getting it in the correct quadrant. Okay? All right. We have about 5 minutes left, and let's be realistic. You're not going to start your homework. So I have a problem for us to close up with. Okay? You have a homework assignment that some of you may do like this weekend, and some of you may do next weekend. If you're one of the people who will do their homework this weekend, you may want to revisit it before you come back next week, because that's giving you like an entire week of in-between time. So at least just look over your homework if you next weekend, if you do it this weekend. Am I making sense? Okay. So, I need you to answer these 4 things. I'm giving you an initial point and a terminal point. I want the component vector, PQ. I want the magnitude. I want the direction angle. And I want PQ in linear combination form. I don't care if you work together at your table, but I need these 4 answered.